Hello everyone, and welcome to a new lecture on engineering economic analysis. This is Payam Parsa from Cal Poly Pomona. Today we're going to talk about the second module of the course, which can be summarized in this statement: what is my money worth to me? And as the first topic of this module, which is discussed in chapter 4 of the textbook, we're going to look at different cash flows and different types of cash flows. And the first one that we're going to look at is the uniform series. And uniform series is very common in practice. We're going to talk about the applications of uniform series cash flow and also solve problems with uniform series compound interest factors and formulas. So this is how a uniform series looks like. The cash flows are distributed uniformly over time, as you can see, and we show them with A here. And there are assumptions for this cash flow. First of them is that future costs and benefits are uniformly distributed. This is the definition of uniform series. And also, these A payments or costs are all occur at the end of each period. So the cash flow in year one or period one occurred at the end of period one. And these A payments are all equal. The applications of them, you can see them everywhere basically. When you take out an automobile loan, you normally pay off that loan over time with uniform payments. So your payments are all equal over time. Or even house mortgages. When you take out a mortgage, you normally pay off that mortgage over many years with equal payments. So these are all uniform cash flows and can be represented this way. So let's look at this very small example here where we have a cash flow of 4 years, and what you can see are these A receipts, and there is a future value associated with this A receipts over time. One thing that is important here is, as I indicated earlier, these A receipts are all occurred at the end of each year. So basically the first A is when December 31st reached and before January 1st of the next year. So these are all end of period cash flows. And if you want to compute the future value of this cash flow, these 4A payments, what would you do based on what you've learned so far? We've talked about time value of money in the previous module of the course. So now, using the formulas that we talked about for present value and future value, you can easily compute the future value of these 4 payments. I want to give you a few moments to think about how you can compute that future value. So what we can do here is to basically consider these A cash flows as individual cash flows and basically treat them as individual cash flows and compute the future value of each of them by considering them as P or present value at that time and computing the F value of that and then summing them up. This is a simple way to approach this. And this is an approach that we're going to use in order to derive a formula for F for a uniform cash flow. So let's look at this general uniform cash flow here. So how can you write F in terms of A here? So I'm going to start with writing F in terms of A here. So the first one here is A times 1 plus I, the interest rate, to n minus 1, because there are n minus 1 periods here between the first cash flow and the future value, plus for the second one is A times 1 plus I to n minus 2. And we're going to repeat this for every one of these cash flows. The last one is a times 1 plus I to 0, which is essentially 1 here. So doing that, we can rewrite this future value as a plus a to 1 plus I all the way to a times 1 plus I to n minus 2, and the last term is a times 1 plus I to n minus 1. So what we're going to do is, let's call this equation equation 1, and we're going to multiply equation 1 by 1 plus I. We're going to multiply both sides of this equation, both f and this side, by 1 plus I. So that is going to be f times 1 plus I is equal to a times 1 plus I plus a times 1 plus I to 2 all the way to a times 1 plus I to n minus 1, and the last term would be a times 1 plus I to n. And also let's call this equation equation 2. What we're going to do is to subtract equation 1 from equation 2. So 2 minus 1. That would be, many of these terms would cancel out. For example, this one would cancel out with this one, and the rest of them actually, this one with this one. So what you will be remained with would be f times 1 plus I minus f, this is the left side of these two equations, equals a times 1 plus I to n minus a. So this is what we're going to be remained with. So the left hand side would be f I essentially equals a times 1 plus I to n minus 1. And as the last step, f would be equal to a times 1 plus I to n minus 1 divided by I. And this is the formula of a uniform cash flow, a uniform series. So essentially this would be the factor that you can read from the table. This is equal to a times f given a I n. And this factor is called uniform series compound amount factor. So this is the formula for computing f in terms of a for specifically a uniform series. And this is what we have here. You can see the formula and the factor that we computed in the previous slide here. and the factor that's called uniform series compound factor. So what we can do here is to basically rearrange the same formula and compute A in terms of F. Now A is equal to F times this factor, and this factor is A given F, and it's called uniform series sinking fund factor. And a sinking fund is a fund into which you make uniform series of money deposits to accumulate a desired future sum by the end of any year. And that's why it's called sinking fund factor. That's where it comes from. What we can do also is to basically substitute F with its definition in this formula. Because we know F is, in terms of P, is P times 1 plus I to N. So if we substitute F in this formula with its definition, we can find the formula of A in terms of P, which is going to be this formula. And the factor associated with that is A given P. And this factor is called capital recovery factor. And this one is also called capital recovery factor because a amount of money have to be earned over time to recover the P capital investment, and that's why it's called capital recovery factor. So there are some critical assumptions for all of these formulas to be valid. First is A occurs at the end of the first year, so this is the first A that has to happen at the end of the first year, and the last one also has to happen at the end of the nth year. So F occurs at Tn, and P also occurs at T equals 0. That's the present worth. Always is at T0. So these are the critical assumptions for the formulas that we derived so far. It's important to know the relationship between these factors. F given A factor is the inverse of A given F. And this is true for F given P versus P given F, and P given A versus A given P. These are all inverses of each other. When you find one, by inversing, you can find the other. So these are the relationship between these factors. So let's look at a few examples here. There are 4 examples in this slide deck, and this is the first one. I'm going to work on the first 2 and leave the last 2 for you as homework. This one says, what equal annual series of 10 payments must be deposited into a fund earning 8% interest to accumulate $12,000? Draw the cash flow diagram and use the appropriate formulas. So by reading the problem, we are essentially looking for equal annual series. So we're looking for A, and the number of periods is 10. The interest rate I is 8%, and what we want to have is to accumulate $12,000 at the end of the 10th year. So this is our future value. So to write what information we have, N is 10, we're looking for A, I is 8%, and F is $12,000. So to draw the cash flow of this problem, we are looking at 10 years. So 1, 2, all the way to 10. And in each year, we are having equal amount of payments. And we're going to call that A. At the end of the 10th year, there is a future value equivalent to the payments that we made. And what we're looking for is A, right? So we know the formula for computing A in a uniform series, right? A is equal to F times I over 1 plus I to N minus 1. So this is equal to 12,000, which is our future value, times 8% over 1.082n, which is 10 minus 1. When you compute this, this is equal to 828.35. The other way to compute a here is to basically use the factor. And in order to do that, a is equal to f times a given f 8% and 10 periods. So if you go to the factor tables at the end of the book, or use the slide deck that I posted on Blackboard, you can read this factor from the table. When you go to the 8% table and look at the row of n equals 10, you can read a given f factor, and that's equal to 0.069. So that's equal to 12,000 times 0.069, and that's equal to $828. So there are two ways to compute a for this, using the formula or using the factor table, and we went through both of them. Let's go ahead and look at the next example here. The next example is a little more sophisticated. This one is saying a new engineer wants to save money for down payment of a house. The initial deposit is $685 and $375 deposited at the end of each month. The savings account earns interest at an annual nominal rate of 6% with monthly compounding. How much is on deposit after 48 months? Draw the cash flow. So there is one initial deposit of $685, and then there are essentially 48 payments of $375. And the interest rate here is given annually, but the compounding structure is monthly. So what we need to do is to use a consistent interest rate with the interest period. The interest period is a month, but the rate is annually, so we need to change that to a monthly rate. So the I that we would be using is 6% divided by 12 in order to have the monthly rate. The cash flow of this problem, let's go through that. We have 48 periods, so starting with 0, 1, 2, 3, all the way to 48. At 0, we're depositing $685, and each month we are paying same amount of money, right? And that is equal to $375. And what we're looking for is the future value at the end of the 48th period. What is that? So essentially it's the same process that we went through in the previous example, but this time we have a uniform series from period 1 through 48, but there is one initial payment of $685 as well. So the future value for this one would be a summation of the future value of $685 and also future value of this uniform series, right? So 1 plus 2 is what we need to look at here. F, or future value in total, would be equal to $685 685 is present value, so we can multiply that to f given p of 0.5% and 48 period. We need to add that. We need to add part 2 to this. And part 2 is a uniform series of $375. And since this is a uniform series, we can use the f given a factor of the same interest rate and 48 periods. And when you read these two factors from the table, you see that the first one is 1.27 and the second one is 54.098. These two factors can be read from the same table because they have the same interest rate. So when you go to the 0.5% interest rate table, you can read these two factors, f given p and f given a, in the row associated with n of 48. So when you do the math here, you get the future value of $21,000, 156. We could also use the formulas instead of factors, and we know the formulas for f given p and also formulas for f given a. I leave that for you guys to work on your own. So there's two more examples. This one, I will leave that for you to work as homework, and there's also this one that is more interesting, and we will discuss that later. But before we wrap up here, I just want to give these useful tips here. You can move a cash flow forward by multiplying that cash flow to 1 plus I, or basically you can move it back by multiplying to 1 plus I raised to -1. And these are for just one time period. And these are intuitional, and you probably realized them before when we talked about the time value of money in the previous module. But I just wanted to reiterate them here. And it's important to know that cash flows cannot be added together unless they occur at the same time.